Hey, last time we talked about the comparison test and we mentioned that it's only useful in certain situations. Well, the limit comparison test won't be useful in every situation, but there will be situations where you can't use the comparison test, but can use the limit comparison test. Let's take a look. Let's start with this example. The sum n equals 2 to infinity of 1 over n squared minus 1. Once again, I'm starting at 2 because I want to avoid the situation where the denominator would be 0 when n is equal to 1. And if you think about what happens when n gets really large, n is 17 trillion. Well, 1 over 17 trillion squared minus 1 versus 1 over 17 trillion squared. Hardly any real difference there. And you would expect this series to behave very much like the series 1 over n squared, which we know converges. On the other hand, we can't use the comparison test here, because to use the comparison test, we'd have to show that the terms of this series are less than the terms of the series 1 over n squared, but they're not. It's exactly the opposite. The terms of the series 1 over n squared minus 1 are larger than the terms of the series 1 over n squared. And since the series 1 over n squared converges, we can't use the comparison test to say that the series 1 over n squared minus 1 converges, even though we certainly feel like it ought to converge. And here's where we need the limit comparison test. And here's what it says. It says, suppose you have two series, both of which have all positive terms, and you look at the limit as n goes to infinity of the terms of one series divided by the terms of the other series, so a sub n divided by b sub n, and that limit is non-zero and finite, so any finite number not zero. Then the two series either both converge or both converge. In particular, you will know what one of them does, and you're trying to test what the other one does. This says they do the same thing. They both converge or they both diverge. Let's see how that helps us with the series that we were just looking at, and then we'll go through a quick proof of the limit convergence test. We'd like to compare this series to the series sum 1 over n squared. And so we look at the limit as n goes to infinity of the terms of one series divided by the terms of the other series. And it doesn't matter which one you put on the top and which one you put on the bottom, because if you're going to get a non-zero finite number as your answer, then the reciprocal of a non-zero finite number is still a non-zero finite number. And after you do a little algebra to simplify that fraction, you get the limit as n goes to infinity of n squared minus 1 over n squared. And there's more than one way to compute this limit. One way is through using algebra and the limit laws. And that's what I've done here. I've divided the numerator and the denominator by the largest power of n in the denominator, so that's multiplying numerator and denominator by 1 over n squared. And that gives us the limit as n goes to infinity of 1 minus 1 over n squared all over 1. And then you apply the limit laws, and you get the limit of the numerator divided by the limit of the denominator. And when you simplify, that gives us a limit of 1. Just to review the other easy way to find this limit, we could use L'Hopital's rule. As n goes to infinity, n squared minus 1 over n squared is of the form infinity over infinity. And so L'Hopital's rule tells us that this limit is equal to the limit as n goes to infinity of the derivative of the numerator divided by the derivative of the denominator. And both those derivatives are 2n, and 2n over 2n is equal to 1. So either way you compute it, this limit is equal to 1. And in particular, it's not 0 and it's not infinity. And so we're ready to give our answer to the problem. We say, since we know that the sum 1 over n squared converges, and you can refer to the p-test here, this is a p-series with p equals 2, we know that sum 1 over n squared minus 1 converges by the limit comparison test. Okay, returning to our statement of the limit comparison test, let's see if we can come up with a quick proof. We'll start by assuming that the limit as n goes to infinity of the terms of a sub n divided by the terms of b sub n is equal to some number c, where c is not 0 and not infinity. I want to pick two numbers, lowercase and uppercase m, such that c is strictly between them, two positive numbers. And since a sub n over b sub n converges to c, that means if we go far enough out in the sequence, past the capital nth term for some number capital N, then these terms a sub n over b sub n are arbitrarily close to c. And what do I mean by that? Well, at least we can make sure that they are between lowercase m and capital M. Now, if we just multiply that inequality by b sub n, we get that little m times b sub n is less than a sub n, which is less than capital M times b sub n, for all n greater than or equal to capital N. And here's the punchline. If the series b sub n converges, then so does the series capital N times b sub n, since it's just capital M times the series b sub n. You can pull the constant outside of the series. And the terms of the series a sub n are less than the terms of the series capital M times b sub n, and that would mean that the series sum a sub n converges by the comparison test, since its terms are all less than the terms of a known convergent series. And similarly, if the series b sub n diverges, then so does the series sum little m times b sub n, because again, you can pull the constant outside of the series. And the terms of the series a sub n are larger than the terms of the series little m times b sub n. And so the series a sub n diverges as well, again, by the comparison test. Okay, let's do a couple of examples. I'll do this first one and leave the next one for you. And so we're looking at this series right here, and the trick is to try to decide what do we want to compare it to. And the thing to consider is that as n gets very large, it's the largest power of n in the numerator and the largest power of n in the denominator that dominate what's going on. In other words, if n is 1 trillion, well, 1 trillion cubed is a big number. 1 trillion squared is a small number too, but it's 1 trillion times smaller than 1 trillion cubed. And so really, it's the n cubed in the numerator and the n to the fourth in the denominator that are controlling how this series behaves as n gets larger. And if you ignore everything else, then what you've got is 5n cubed over n to the fourth. The 5 certainly doesn't matter. You could pull that out. And n cubed over n to the fourth is 1 over n. We know that the series 1 over n diverges, and so we would expect this series to diverge, and the right series to compare it to would be the series 1 over n. And so we look at the limit as n goes to infinity of the terms of the series that we are trying to test divided by the terms of the series that we're testing it against, so divided by 1 over n. And this is just about the last time you'll see me write this in this form. Dividing by 1 over n, same thing as multiplying by n over 1, and so I will usually skip this quadruple decker fraction step and go straight to the next one, which is this, and then you can distribute the n in the numerator, and you get this limit here. And then either by applying algebra and the limit laws or L'Hopital's rule, you take this limit and you find that it's equal to 5. So I'll let you fill in the details, but the point is that 5 is not 0 and it's not infinity. Now we can conclude that since we know that the series 1 over n diverges, the series that we're looking at also diverges by the limit comparison test. Okay, it's very important to choose an appropriate series to compare to. Before I give you one to try, let's see what would have happened had I tried to compare this series to the series 1 over n squared. Well, then I would be looking at the limit as n goes to infinity of the terms of this series divided by the terms 1 over n squared, which is the same thing as multiplied by n squared over 1. And after you distribute in the numerator, you get the limit as n goes to infinity of 5n to the fifth minus n to the fourth plus n squared, all divided by n to the fourth plus 6n plus 3. And you could divide numerator and denominator by n to the fourth and apply the limit laws, or you could use L'Hopital's rule. You'd have to use it 4 or 5 times, but one way or another, you would get that this limit is equal to infinity. And what does the limit comparison test say when the limit is infinity? The answer is nothing at all. It only tells you what happens when the limit that you get is non-zero and finite. Here we got an infinite limit, and so the limit comparison test tells us nothing. In particular, what this means is we compared to the wrong series. Had I done it the other way around and did 1 over n squared divided by the terms of this series, then the limit I came up with would have been 0, and we've been in the same situation. The limit comparison test doesn't tell you anything. Moral of the story, if you apply the limit comparison test and you get a 0 or an infinity for your limit, then you've compared to the wrong series and you should start over. Okay, you try this one. Sum n equals 1 to infinity of n plus 1 over n cubed minus n squared plus n plus 1. Take a moment, try to determine what series you would compare it to, and apply the limit comparison test and see what you get. So pause the video, and when you're done, start it back up. Considering the largest powers of n in the numerator and the denominator, you would want to compare this series to the series n over n cubed, which is 1 over n squared, and you know that the series 1 over n squared converges. If you wanted to try to use the comparison test, you'd have to try to show that the terms of this series are less than the terms of the series 1 over n squared, which seems very unlikely and would be very difficult to show. It's probably not even true. And so we look at the limit as n goes to infinity of the terms of this series divided by the terms of the series 1 over n squared, which is the same thing as multiplying by n squared over 1. And after you distribute in the numerator, you get the limit as n goes to infinity of this expression right here. And then you can either divide numerator and denominator by n cubed and apply the limit laws, or you can apply L'Hopital's rule 3 times, and one way or another, you get that this limit is equal to 1. And in particular, it's non-zero and it's finite. And now, to finish the problem, we can conclude that since we know that the series 1 over n squared converges, because it's a p-series with p equals 2, that means that the series n plus 1 over n cubed minus n squared plus n plus 1 converges by the limit comparison test. Okay, that was the limit comparison test. It's a little bit more difficult to use than the comparison test because there's a limit that you have to compute, and I will expect you to actually compute the limit and come up with a number if you're going to use the limit comparison test. But there are situations where you simply can't use the comparison test, and the limit comparison test comes to the rescue. So there's a homework on this stuff. Give it a try, enjoy it. Look forward to seeing you in class.